So to start with, we'll start with from where we have left in the last class. So in the last class, we discussed certain things about diffusion and then the ion implantation, isn't it? So the ion implantation, as I have already told you, that it is the process which is done at room temperature. Okay, and it requires a process which is called as annealing after completion of this ion implantation. So after ion implantation, you require a process which is called the annealing. So in the annealing, you just heat the wafer once again, but at a certain low degree, low temperature. So it is up to 400, 500 degrees centigrade somewhere, and this gives you better like control over the profile which you want to dope. So that is what the biggest reason of doing the ion implantation, but it is not still perfect. And though I mean, like out of all the other methods you have to put the material inside the substrate, this is the best one. Okay, so far. So this is the one of the method, ion implantation, and this particular method is like more useful for your MOSFET devices. So when this method was not invented, till the time people were not able to fabricate the MOSFETs. Although BJTs were able, they were able to fabricate, but not the MOSFETs, because in MOSFET you require a very precise control of the threshold voltage, particularly in the channel region. So you have to like do make the channel like threshold voltage implant. Okay, so that is called as threshold tethering. So you need that as well. Apart from that, you also need the other things like the channel stop implant. Okay, so this we have seen earlier when we were discussing the various type of capacitors. So that time we have seen that in case of like a dynamic capacitor was there. So that dynamic capacitor is like how to control that. I mean, how get affected. So the channel stop implant is also required. So this is only possible with ion implantation. Okay, so this gives you very precise control of the various parameters you can control. So now let's discuss some of the things, some of the properties of the silicon dioxide, because this we will require. But this I think we should discuss a little bit later. Silicon nitride. Achha. So it's good to discuss this here only. So you see, next step we will require will be like deposition. So before deposition, I mean deposition, we do deposition of various materials onto the silicon substrate. So the first material usually we deposit or grow is sometimes we have to grow or sometimes we have to deposit, okay, depending upon the requirement. So if you have to grow or if you have to deposit the silicon dioxide, so what are the reasons because of which we use the silicon dioxide? And apart from that silicon dioxide, we have to use the silicon nitride as well. Okay, and this deposition also require we have to like silicon nitride can't be grown; it has to be deposited. Okay, and the other things like aluminium. Okay, so when you have to make the metal contacts, so that time also you have to like deposit the aluminium first. So let's see the properties of this silicon dioxide and then the silicon nitride, because they becomes the important material to like uh, to protect the device. So the first thing is this SiO2 is usually used.
Excuse me, sir.
Yes, please.
Sir, are you changing the slides because iron implantation is visible
Okay, okay.
for
So
us?
properties of silicon dioxide is not yet visible to you, huh? That's
No,
now
sir.
is it?
Yes, sir.
Okay, so I'll keep it in this mode only, because if the slide is not changing, so it's good you have like told me in the beginning only. Okay, so just change. I mean, just tell me if it is not changing. Okay, I mean, I think it is changing now, right? Is it changing? Silicon nitride it is showing.
Yes,
Okay,
sir.
fine. So I'll keep it in this mode only. Maybe some reason that in the full screen mode it is not doesn't change, or like what, I don't know. I have to restart the system. So you see, this SiO2, one of the few properties which becomes important for VLSI is that it provides a very good insulation. Okay. And the other thing is that it also works as a mask. Okay. So sometimes when like you have to when you expose certain materials to the wafer, then if the oxide layer is there, then the material do not get penetrates from that region. So you have to remove that oxide to open a window to make to implant or diffuse that material inside that to put that material into the wafer. So it have some and good quality of the masking also. So this is another reason which you use because of which you use this SiO2. Then there is another reason that you use this SiO2 is it is like it adheres well. Okay, the adherence coefficient of the material is quite better than the other materials. Okay, so because if it is not adhering properly to the surface, then there will be like there'll be problems into the circuit. The circuit won't work properly because for insulation there should not be any gap, any gap between the two layers. Okay, so that is what the adherence should be proper. Okay, then the other material which you use usually for protecting the device is the silicon nitride. Okay, silicon nitride is used as a gate material also. Okay, to not as the gate material basically, but as the silicon dioxide. So instead of silicon dioxide, you sometimes use silicon nitride because in some of the processes which you will study later, like locos is one of the process where we require this silicon nitride instead of silicon dioxide. Okay, because it is possible to make very thin layer of silicon nitride. And the other thing is it gives you it is oxide resistant as well. So if once the silicon nitride is formed, then if the material is exposed to oxygen ambient, then also the silicon dioxide will not be formed. So in some of the processes where you don't want silicon dioxide at that time, okay, because if the oxide if the if there is a little bit oxygen even present in the ambient, then silicon dioxide can form and it can deteriorate your the device parameters, okay, the device performance. So to control those things, you sometimes require even to control the oxide also. Okay, so silicon dioxide should not be formed. So at those places, we use silicon nitride. So how the silicon nitride is formed? We use basically the silane. So silane is this SiH4. There's various like combinations of Si we use here. So SiH4 is one of this, and when it reacts with your HNO, this NH3, so then it gives you the silicon nitride and the gas which is like hydrogen, so which is volatile. Okay, and the reasons which I have told you earlier, that why we use this silicon nitride, and it works as an insulator. So it is a very good insulator, in fact. So the next step which we have to see is the deposition. So the deposition, as I have already told, that we have to deposit SiO2 sometimes. Then deposition is like what, first of all? So deposition is forming a layer over a surface, okay, or like forming a layer over the other layer, okay, depositing a layer of certain material over the other material. So that is called as the deposition. So deposition, you have to deposit you may require to deposit anything. You may require to deposit sometimes multiple metal layers. Sometimes you have to deposit this nitrides, the oxides, and sometimes you have to even deposit the polysilicon. Instead of the metal, you use sometimes the polysilicon. There are reasons that why you use polysilicon that we will see later. Okay, and to deposit various materials, we have certain methods as well. So the various methods to deposit the material over the substrate or over the another layer. There are various methods which each method have its own advantages and disadvantages. So the first method is what is known as CVD, is chemical vapor deposition. So this chemical vapor deposition, the name itself suggests, most of the times the name is self-explanatory. So you understand that chemical vapor deposition, in chemical vapor deposition, there is a chemical reaction which takes place. So what we do is like we take some chemical and we vaporize it, okay, at and then that heating, the temperature, it should be like the temperature, it should the process should go at the temperature where this chemical should vaporize. So once that vapor is that chemical is vaporized, then the vapors of that material, okay, is like condensed on the surface. So you keep the substrate at lower temperature and the ambient, the surrounding at a little higher temperature. So then what happens? Because of the low temperature of the substrate or whatever layer, the substrate, because the other layers will be on the substrate itself. So you keep it at a certain lower temperature. So then that those vapors get condensed on this material and get deposited. Okay. Or there is like some chemical reactions also that takes place. So chemical vapor deposition is one of the thing. Then the other method is the low pressure chemical vapor deposition. So sometimes we use this low pressure LPCVD. So LPCVD has its advantages. Okay, chemical vapor deposition, problem is it forms chemical bond. Okay, so sometimes you don't want the bonding to take place. You just want the layer to be deposited over the another, because that layer has to be removed after some time. So that chemical vapor deposition, if you do, so this particular method have the disadvantage that it will form some bonds as well, because the chemical reaction will take place. The other method is the low pressure chemical vapor deposition. So in the CVD, we use normal pressure, the room temp, the atmospheric pressure. We work at the atmospheric pressure, but there are certain advantages of like working at the low pressure. So at the low pressure, the reaction rate also becomes fast. Okay. So or the reaction rate becomes also fast, and the quality of the material is also good. So that is what you use LPCVD. So here also the chemical reaction takes place, but again the chemical reaction takes place at a lower at a lower pressure. Then the another method is the plasma assisted chemical vapor deposition, PECVD. So in PECVD, what we do is, rather than using the complete ambient at a high temperature, in the same ambience, we do like temperature difference. So plasma, plasma is like a material in which you have like localized high temperature. Okay. So mostly the temperature will be high, whereas there will be some regions where the temperature will be low. I mean, some regions will be temperature will be very high. Most of the regions, the ambient will be not that high, will not be that at that high temperature. So then you keep that particular substrate in a region where that temperature is very high. Okay. So then you can use this plasma assisted. And with this temperature control, you can control in the plasma. Basically, you have to control the electron energy. Okay, the bombardment energy. So the energy with which the material will get bombarded with the this material. Okay, the substrate. So that, not the substrate, but the chemical which you want to deposit. So you fill or you keep some this chemical into that into a certain chamber, and then a plasma is like flown through it. So then that chemical that quickly that vapors are formed of that chemical, and then later it is deposited onto the substrate. So this is called this plasma assisted chemical vapor deposition, or PECVD. And there is like some other forms of this vapor deposition. One is like deposition. For deposition you use another method which is called as, which is particularly a physical method completely. And in these methods we have seen that there is some chemical reaction which takes place, or in like not all the these methods in which the chemical reaction takes place. The other two methods where you are like talking about the plasma and the low pressure, the chemical reaction doesn't takes place, whereas in the first one the chemical reaction actually takes place. So if you don't want even like just physical method you want, okay, so physical, there is like one more method which I remember is the sputtering. So in sputtering, what we do, we just remove the atoms by continuously bombarding the material. Whatever material we want to just deposit, we just keep on bombarding it with a very high energy material. So then what will happen by just continuous bombardment, that material actually loses some atoms. Okay, and those atoms gets like when settled down on, they are allowed to settle down on the substrate. so uniformly, and that while sputtering, that substrate is continuously rotated as well. So when you spin it, so then the distribution of the atoms is uniform. So it is sort of like, if with an example, if I try to explain, so then what happens? Certain material is there which you want to. This is material which you want to deposit actually. So what you do? You bombard it with a high electron energy. So let's say if it keep on bombarding at a particular location, so you just decide that location where it will bombard. So if it keep on bombarding at that place, okay, hitting at that place, then what will happen? This material will start dislodging from that material, this particular layer, and it will, if like they are in their ambience, and if it is allowed to settle, then because of the, let's say, gravity itself. So if the substrate is lower and you are hitting the material from this region, so then it will, like what happened, they will settle down nature, I mean at the bottom surface. So in sputtering, you just hit the material continuously, which you want to deposit, and allow the atoms later to settle down on the substrate. And while this settling, you also continuously rotate that substrate. So then the deposition is uniform. So these are certain methods for deposition. But then you also require, this is etching. So etching is basically, you use two types of etching. Etching is like removal of the oxide layer. Okay, so etching particularly terminology is used for removal of your oxide layer. So SiO2 layer if is present and you want to remove it, so there are certain methods which are like your dry oxide, this dry etching or the wet etching. So in wet etching, basically we use chemicals, okay, to dissolve the oxide layer. Whereas in the dry etching, we use the materials such as hydrogen or some this vapors of some acids. Okay, and then these acids slowly, I mean, this ionize these gases. Okay, I mean, these ionized gases are there, and they slowly like react with the oxide and like remove the oxide. Okay, so that is what the thing is we do in the dry etching. So wet etching, if you do, so then there will be problem of what we have seen earlier as well, which is called as the isotropic etching. So the chemical doesn't know that in which direction, I mean, what is the difference between the vertical direction and the lateral direction. So with chemical etching, with the wet etching, if you are using, so there'll be like sort of problem of lateral like encroachment. Okay, so there's encroachment under the mask region. So this is what is called as isotropic etching. So you don't want isotropic etching, you want anisotropic etching, that is the etching in the vertical direction only or in the intended direction. So for that, the better method will be dry etching. So in etching, so this is what the basically the purpose of etching is, like removing a certain region. Okay, so for etching, if I just talk, in case of wet etching, you use certain materials which are like which have like chlorine in it. So chlorine or like halogens in it. So chlorine, fluorine sort of materials you use. So HCl you use, okay, or you use HF, something like that, to dissolve that oxide, okay, because later on it will form some oxide compounds and it get dissolved. Hmm? So that is what the purpose of like, so if you just want to remember like in broad terms, so chlorine based materials should be used as an etchant. Okay. Mm, then there is like sometimes you have to grow the epitaxy layer also. This epitaxy layer is prominently used in BJTs, but nowadays in modern MOSFETs also this epitaxy is required. It is required to to remove, I mean, to overcome certain problems, which we will study later on. One of that problem is the latch-up. So if you provide epitaxy layer, so then there will be problem of what is called as the latch-up in the CMOS devices. But if you provide the epitaxy, I mean, this latch-up problem like uh, can be resolved with the help of this epitaxy layer. So if epitaxy layer is already provided into the material, then the device will not have this latch-up problem. Okay, so just wait a minute. I have to, okay, fine. I'll take it later. So for epitaxy, what we do is Epitaxy is nothing, but it is sort of the material. The name itself suggests that the epitaxy is like it is like ordering upon something. So when you have a particular substrate and you want to make a better quality layer over that substrate, the already existing substrate, then you want a more ordered surface. Okay, for device fabrication and for like various regions to control the doping concentration in that particular region, to have the good performance of the device, you want very precise control of the top layer. Okay, so this epitaxial layer is grown for that purpose. So for epitaxial also we use this particular deposition to grow the epitaxial layer, or to form the to form the epitaxial layer over the substrate. We have to use this methods which we have already discussed here. So what are these methods? So those what are the methods? I've just shown you those deposition methods. Right. Huh. So yes, this deposition methods. So these deposition methods you use even for depositing the epitaxial layer. Okay. So there are these methods which you use epitaxial layer. So epitaxial layer is a very thin layer, which is, I mean, it should not be very thin, but it is like if your substrate is of the order of thousands of microns, let's say 1 mm or like half an mm, so 10,000 microns if it is, so then your epitaxial layer will be somewhere around hundreds of like microns. Okay, not angstroms, I'm talking about the microns. So it will be in the order of hundreds or 20s, or I mean in the tens of microns. So use it something like 50 microns or 20 microns, so depending upon the requirement, because your device will be somewhere in the top layer 1 micron or something like that. So that epitaxial layer is a very ordered layer of the silicon. Okay, so this is what the purpose, like epitaxial layer is also there, so you have to grow that epitaxial layer with various processes which you have already seen. Okay, and it is done at a very high temperature because you want very precise control of the silicon dioxide, silicon, not the silicon dioxide. And here the crystal structure should be very like the defects should be minimum. So the purpose is to reduce that complete this defects present in the if there are any defects present onto the substrate. So just to remove them completely, you use this epitaxial layer. Or like if you just can't remove them, then you use a top layer over it, so that in that layer the defects will be very less. So that is what the purpose is. So there are the methods with which you can grow this epitaxial layer. The methods are same. Now let's come to, after like we have discussed almost all the methods. Okay, to the various processes which are required to fabricate the device. And when and let's say when I said the deposition, so I have also said the deposition of the uh, I mean, in fact, the deposition of the photoresist if you want sometimes. So the photoresist deposition is also done by those methods which you have already seen. Okay, and as I have already told in one of the class that photoresist, what you do, you just put the some drops of the photoresist and then spin coat it. Okay, so that is also possible. Apart from that, if you want to use the metallization, so metallization layer is also deposited with the methods, the deposition method which you have seen. Okay, so aluminium if you want to make, or copper if you want to make. Okay, or so that is what the thing is. You use even for aluminium metallization, you use the same methods for the deposition. Now, let's see how to actually make a MOSFET. Okay, so before making the MOSFET, actually the NMOS, we will start with NMOS and the CMOS, not the BJT. So NMOS and CMOS, if you have to fabricate, so how we'll start, what substrate we will take, we'll see that in the next slide probably, in the next or the next slide onwards. But then, okay, so you see, first let me show that, I mean, once again I will show you that what are the photolithographic processes are, because this photolithographic process you have to do them regularly. Okay, I mean, whenever you have to open a window, so this photolithographic process has to be done again and again. So just let's see this photolithography sequence, okay, in short, because in detail we have already discussed this. So what we do is, let's say, initially we have some certain substrate, so that substrate layer is there, and then over that we first have to grow the oxide layer, so silicon dioxide. Then over that you can see that a photoresist layer is grown, okay, is deposited. So photoresist is deposited there. Then after the photoresist coating, what we do, we expose it to the UV light. Then this, through a mask. So the mask is there and it is exposed, the substrate is exposed to the UV light. And because of that, there is some regions which are unexposed to the UV light. So it forms a certain patterned region. So that patterned region looks something like that. So in that patterned region, because the photoresist which you have coated gets softened, so it can be easily like etched out. So the oxide layer along with the photoresist is etched out. Okay, the which oxide, which photoresist, the softened one. So that along with the oxide is etched out, and then you do the ion implantation. Okay, because now the oxide layer, which the photoresist and the oxide layer, which was not hardened, which was not softened, so they remain hard, and they work as a ion. They work as a mask for the ion implantation. Okay, not for the diffusion. This photoresist layer can't work as a can't work as a mask for the diffusion process, but it can work as a mask for the ion implantation process. Why? Because the ion implantation method, the ion implantation process actually happens at the room temperature. So the photoresist can withstand, can withstand this temperature, whereas the diffusion process happens at a very high temperature. So the photoresist will like can't handle that much temperature, and even gets evaporate sometimes or get melts out. Okay, so the ion implantation you do, if you do the ion implantation, then this particular photoresist can even act as a mask. So after that, you do the this doping is done, and then you form a doped layer, doped region here under the this region. So it is shown here somewhere. But it should be like shown completely. So this is what the photolithographic process is. Now, this photolithographic process, with the help of this photolithographic process, we will see the formation of the polysilicon gate. As I have already told you that in the earlier process, let me first tell you that because this polysilicon will be an important material, because wherever we will do the fabrication, we will use nowadays this polysilicon. Okay, not even the metals. So on the gate, for the gate contacts, for to form the gate contact, we don't use the metals. We use polysilicon. So the reason for using the polysilicon, the difference between the polysilicon gate technology and the metal gate technology. So there are two technologies basically defined as. So earlier one was the metal gate technology. So in the metal gate technology, people used to use this aluminum to form the metal gates. Okay, to form the over the oxide layer, over the thin oxide, you have to grow some, you have to make some layer to form the electrical contact. So people used to use this aluminum because of its certain good adherence to the silicon, one of the basic reason. Okay, but there are like problems with the aluminum also. So one of the problem is like electromigration. So which this one of the problem is electromigration. We have already studied when in during the first unit. But there was no like better solution than the aluminum. So aluminum was the best solution. So people used that aluminum to form the contacts and the gate contact, as well as the contact as well as to form the contacts with the other terminals. Okay, source region, drain region, and also that aluminum was used to form the interconnects between the various devices. But then the problem with aluminum was that it does not, you cannot make very small geometry devices, because the basic reason was that that particular technology, you have to first make the source and the substrate regions. Okay, and once that source and the substrate regions are made, okay, then if you grow it to the higher temperatures, if you again put the device at a very high thermal stress, then what will happen? I mean, let's say suppose in that technology, what you do, you make the source and the drain region, and then the aluminum region or the gate region is formed. Now, after the gate region is formed, you again have to form the passivation layer, okay, the oxide layer. Now, if you form the oxide layer, that oxide is actually grown at a high temperature. So what happened if that high temperature process is done after the aluminization? So the problem is like aluminum can't handle that high temperature. So first you have to make the source and the drain regions, and that gate region you cannot control very precisely. So because of that, the aluminum gate, with the aluminum gate technology, we were not able to get very small geometry devices. So rather than that, people have invented this polysilicon gate technology. In the polysilicon gate technology, this polysilicon is basically have the property of like self alignment. So in the self alignment, what happens that if you first grow the polysilicon, then automatically the source and the drain region will be aligned with each other. You don't have to align them like with the help of a mask. Okay, so you can this becomes very easy to like isolate the very small devices also. Okay, so that is what the reason that the polysilicon gate technology is nowadays used. Okay, so it have the best advantage of, I mean, the best thing which this polysilicon gate provides is like self alignment. Okay, apart from that, the it works as a like polysilicon, so you have some doping into it. So because of that, it like works as a conductor. So in case of polysilicon also, what we do, we use some substrate and then this SiO2 layer. Okay, so over the SiO2 layer, let's say this is the thin oxide. So over the thin oxide, I will grow this polysilicon metal contact. So once this photoresist is this polysilicon is grown, then you grow the photoresist. Okay, then you expose it to the UV light. Okay, through the mask. Then what will happen? This polysilicon, wherever it is like exposed, okay, so it gets softened, whereas it is not wherever it is like uh, not exposed, so that particular thing is hardened. So you remove that softened pattern and you form uh, this is the mask. So this dark regions, you can see that the light will pass through it. Okay, so basically that should have shown inverted. So you see this particular thing will get later dissolved and you form this pattern here. Okay, so you will see that this particular thing will be used, this polysilicon will even used as the interconnect also. Okay, not only used at the metal at the gate level, at the to form the gate contacts or the source and the drain contacts, but it is also used to form the interconnects. So with this background, let's start fabricating our NMOS. So we'll see this process in detail. So to fabricate our NMOS, basically in the polysilicon and this polygate technology. So what we have is the substrate first of all. So silicon substrate we have. Okay, so that the substrate which we have bought from the market. Okay, from the vendor. So this substrate should be of 100 orientation. For particularly for MOSFETs, you require 100 uh, oriented wafers. So why this 100 oriented wafers you require? Whereas for MOSFETs, whereas 111 oriented wafers for your BJTs. The reason being, this 111 oriented wafer is particularly like not that costly. Why it is not costly? Because it is easy to grow the 111 oriented like wafers. Why it is easy? The basic reason is like when you have the surface 111, the distance between the crystal, the distance between the surface, okay, the surface is very small, and if the distance between the surface is very small, the adherence to the material is very good. Okay, if you put the 111 seed in the Zagorowski process, then you can easily form the pure crystal. So that is what the basic reason, that earlier when the BJT was fabricated, when the MOS, when the ion implant technology was not invented, so people were not able to fabricate that MOS. So at that time, when the BJTs were fabricated, that 111 had worked very well. Okay, but when you try to fabricate the 111, I mean, when you try to fabricate the MOSFET on the 111 substrate, then its performance is not good. Why? Because as I have told you, that the distance between these surfaces, okay, the adjacent planes, I should say, okay, not the surfaces, the adjacent planes adjacent crystal planes is very less. And because these MOSFETs are going to be the surface devices, and in this surface you want like some space between the layers to move the charge carriers, okay, particularly the enhancement type of devices. So that is not possible with this type of the performance was, I mean, you were not able to fabricate it. So then people thought about the various orientations and the 100 orientation. In the 100 orientation, basically the spacing is little large compared to 111 orientation between the adjacent surfaces. And because of that, what happens? The charge carriers are able to move smoothly between the source and the drain regions. The planar device will be more efficient. So that is what the reason people started. People use 100 orientation for the basic reason, okay, for fabricating the MOSFETs. Apart from that, it has certain other advantages as well, but this is the basic reason. So then once you make this, once you have the silicon substrate, then you grow a silicon dioxide over it. So silicon dioxide, so to grow the silicon dioxide, what we do, we just expose the substrate to the oxygen ambience. uh, it should be like at high temperature, so then the quality of the oxide will be little better than what you grow at the room temperature, okay. And this oxide is called your thick oxide, let's say. The thickness of this oxide is somewhere around 8,000 angstroms, 8,000, 10,000 angstroms, okay. So you grow an oxide layer. Once the oxide is grown, then what you do, you open a window with the help of photolithography process, okay. So the processes which I have not which I have just shown you earlier, the photolithographic processes in the previous slide, in this particular slide. So these all processes are used to open a window. So this particular, you can see that a window is open here, okay. So window is opened here. So that window opening is done with the help of this particular thing, and you see the etching is also done. So etching process is also you have used, and completely this particular thing is open to you. But you are not using diffusion process, okay. So ion implantation is not used here. So just the window is open. So now once the window is open, then in case of polysilicon gate technology, what you do is you first step is to fabricate the gate, okay, the gate region, to form the gate region. So see this, the thin oxide is deposited. Now the thickness of the thin oxide, why we are calling it thin oxide? Because the thickness of this layer, thin oxide, is like approximately 10% of the thickness of this uh, SiO2 layer. So if SiO2 layer is somewhere like it is 10% or 1% around. So you see, if this is like 8,000 angstroms, then this will be around 80 or 100 angstroms. Okay. So this is this thin is very thin. Okay. So it is like hundreds of angstroms you use. So that is why it is called thin oxide. And this thin oxide is basically grown with dry oxidation process, okay, not with the wet oxidation. SiO2, this thick oxide you can grow with wet oxidation, because you don't want it to be that high quality. It will be just used for insulation, whereas the thin oxide have to actually handle some electrical stress as well, so its quality should be better. Because here actually you the basic the MOSFET capacitance which you are going to form, the capacitance which will give you rise to your this device will be because of this thin oxide. So this thin oxide should be very of good quality. So that is why this dry oxidation process is used to make this thin oxide. Once this thin oxide layer is formed, then over that you use a polysilicon layer. So polysilicon is basically will help you to form the contacts. So why the polysilicon is used? As I have told you, that this polysilicon will give you the advantage of self-alignment. So if your devices are very small, then you can like easily self-align them. The source and the drain region, there will be no like problem of merging the source and the drain region together. If your mask get little misaligned, because this device geometry is very small, okay. If you talk about the long devices also, they are very small, as I have shown you in the very initial lectures, that how small these devices are. And if these devices goes at the some micron level, then to control the source and the drain regions becomes very difficult, okay. So you want a certain process in which the devices should be like automatically the source and the drain region should be found in that region only. There should not be any chance of forming it at like misaligned regions, or certain other regions which you have not desired. So that is why you use polysilicon. So polysilicon gives you the advantage of self-alignment, and because of this only, very small geometry devices are possible. So first you deposit the polysilicon, and then with the help of photolithography, pattern it, and just leave this in this region where you are going to form the gate region, whereas you remove it from the other regions. So the polysilicon is removed. Okay. So I'm not showing that photolithography process again and again. Okay. Just when I'm like, whenever I'm showing a certain layer and removing the other layers, it is just because of the help of that photolithography and the etching and all those things only. Okay. So after this polysilicon, what we do? We remove this oxide layer, the thin oxide layer. So once this thin oxide layer is removed, then you open a window here in this region. So in the silicon substrate. So this region is now where you have to like make the source and the drain regions. Okay. So the source and the drain regions are made in this. So it is basically you provide the diffusion. So you make these regions by the help of either diffusion or the ion implantation. So if the device is very small geometry device, then you go for ion implantation. If it is not so, then you go for diffusion. Why diffusion and like why ion implantation? We have already discussed the advantages of diffusion and ion implantation. So diffusion basically will have some lateral diffusion as well. It will not have the diffusion in the vertical direction only, but also in the horizontal direction. So there will be some encroachment under the gate, okay, and under the source, under this oxide layer as well. Whereas if you use ion implantation, the encroachment will be very, very less. Okay, it will still be there because you see that ion implantation. If you do the ion implantation, after that you do the annealing, because the ion implantation damages the surface, because if the high electron beam is continuously impacting that region, then what will happen? The crystals will get like distorted. Okay, the crystals will get distorted in this region. So they'll be like the surface will not be useful at all. So again you have to do annealing process. So when you do annealing, and that annealing is like somewhere around 400 500 degrees centigrade, so what happens? Some diffusion will take place. Okay, so this particular, that's what I'm saying. In case of ion implantation also, there will be some like lateral like encroachment under the gate and the oxide region, but that encroachment will be far less compared to the encroachment which you have which happens in case of diffusion process. So that is what the thing is. Okay. So once that is done, once the source and drain regions are formed, so these regions, like you are forming the NMOS, so you will dope it with N plus, let's say. So this N plus, these regions will work as source or drain, depending upon how you apply the voltage. So that is another issue, that which one will work as a source and which one will work as a drain. But basically, of these regions you form. So once these regions are formed, then you again grow this oxide layer. Okay, this insulating oxide is like again grown, so to protect it back. Okay, because once this is grown, then what you have to do is you have to protect these regions. So once this protected, this particular complete gate oxide is protected, then you have to open these windows. So open these windows in this region. Okay, so this open windows, now you can form the metal contacts in this region, because now you have like what, this connection should be there. So you protect the polysilicon as well. Okay, then you form this polysilicon, and this particularly windows are opened, and once these windows are opened, now you have to form the metal contacts. So this polysilicon gate is formed here, or you can use it here. So now you see this polysilicon gate is insulated in this region, and in this technology particularly we are using aluminum contacts, whereas nowadays people also use polysilicon interconnects also. Okay, so polysilicon interconnects can be used, but to here we can see that the metal contacts are formed here, and this insulation should be provided to separate the source and the drain regions from each other. Okay, so then the this metal deposition is done, right? So this is how you form the complete device. So you can see that the complete device in which you have the metal contacts for your this source and the substrate, and the polysilicon gate for your this gate terminal, right? So this was about the NMOS fabrication. There are some of the things still remaining, that, I mean, the time is about to over. So those things I think we will discuss in the next class. The CMOS fabrication. We have just seen the NMOS fabrication. We will see the CMOS fabrication in the probably in the next class, and the other isolation techniques, some of the isolation techniques which we have to use to isolate one device from the another device. So that we will see in the next class. So if there is any doubt to anyone, let's try to clarify it. So any doubt to anyone? Please.